More one-dimensional motion examples. We have a car with good tires on a dry road that can decelerate at about 5 meters per second squared when braking. If the car is traveling at 89 kilometers per hour, how long does it take for the car to stop under these conditions, part A? Then part B says, how far does the car travel during this time? So let's start listing some things. I drew a picture. My car's traveling one way. I'm told that the car decelerates at 5 meters per second. So if my car is traveling towards the right, and that's the positive direction, deceleration implies that my acceleration is in the opposite direction. And so my acceleration is actually negative 5.0 meters per second, which implies a magnitude of 5 meters per second squared in the negative direction. The next thing I need to do is take 89 kilometers and convert it to meters per second. So kilometers per hour is actually 89,000 meters per 3,600 seconds. When I simplify by dividing the top number by the bottom number, I get that my initial velocity of the car is actually 24.72 meters per second. Part A asks us, how long does it take for the car to stop under these conditions? So what we're going to do is we're going to figure out the time that it takes the car to stop. So with an initial velocity of 24.72 meters per second, and then an acceleration or deceleration of negative 5.0, I got to pick an equation. Now, I'm probably going to go with V final velocity equals V naught plus AT. And if it tells me that the car is going to stop, that means that the final velocity would be 0 meters per second. So my final velocity is 0, which is equal to the initial velocity, which is 24.72, minus the acceleration 5 times t. Now it's just an algebra problem. I move 24 over to the other side, then divide by negative 5. And when I'm done, after I've solved for t, I'm going to get that it's going to take me about 4.9 seconds to get the car to slow down with the deceleration of negative 5 meters per second. That's part A. It asked me how much time did it take for the car to slow down. Part B wants to know how much distance has been traveled by the car in that time of the 4.9 seconds. If we look on page 57 in our textbook, there's a whole bunch of kinematic equations that we could use to solve for delta x. For example, I could say delta x equals v naught t plus 1/2 at squared, but that's a lot of work. So what I'm going to do is I'm going to try and find one equation that doesn't have as many variables, that might be a little bit easier for me. That would certainly work though, because I know velocity and time and the acceleration. But another equation that I might use is 1/2 times v plus v naught times t. Well, since the final velocity is 0, this is really an easy problem where I just plug in some numbers and multiply. So delta x is equal to 1/2 times 0 plus 24.72 times 4.9. And if I just plug that into my calculator, 1/2 times 24.72 times 4.9, I get that my displacement, or delta x, is actually going to be approximately about 61 meters. And so to kind of recap what we've done here, we just needed to find out how much time it took for the car to slow down and how much distance was traveled by the car in that time. So again, we have a car that takes off or is traveling at 89 kilometers per hour, which is actually 24.72 meters per second, with a deceleration of 5 meters per second. With that deceleration, it takes 4.9 seconds to slow down to a final velocity of 0, and the distance traveled by the car in that time is actually about 61 meters. And that's pretty much all we had to do for that problem. A couple of things that I'd like to point out, I guess, is that we can orientate our velocity vectors. Usually I just like to keep it in the way that the number line goes. Going to the right is positive, going to the left is negative. When we decelerate, we go in the opposite direction of the velocity. Once we list all of our variables, we plug them into the equations, and that gives us all the answers that we need. Okay? Next up, we have a car that's moving at 110 kilometers per hour. And the question asks, how long does it take to travel 25.5 miles? And then if it stops in 35 seconds, what is the average acceleration to slow it down? So I have my little car here, and I'm going to draw a picture to kind of orientate all the things that we need to take care of. The picture helps kind of organize the data in my mind. Remember that velocity and acceleration are vectors, so it's important to kind of consider which direction is positive and which direction is negative, because the car will slow down. Also, we need to do some conversions. We're given that 110 kilometers per hour. We always want to fix that or change that to meters per second. So remember that 1 hour is equal to 3,600 seconds and 1,000 meters is equal to 1 kilometer. After we do our conversions, we end up with 110,000 over 3,600, and that's 110,000 meters over 3,600 seconds. To convert that by taking the top number and dividing it by the bottom number, we get that our initial velocity is about 30.56 meters per second. Next, we need to convert 25.5 miles into meters. So remember that the conversion factor is 1 mile is equal to 1,609 meters. So when you multiply across the top, you get our displacement delta x is equal to 41,029.5 meters. Part A says, how long did it take to go that distance? So we're going to need a time. And then for part A, it doesn't say anything about acceleration, so we have to assume that the initial velocity is the same as the final velocity. And so I have two velocities, delta x and t. I'm going to pick a kinematic equation that I could plug those values into and solve for t. Now it's true part B talks about stopping, and that would imply that there's deceleration, but right now we're only working on part A, and that implies that the two velocities, both initial and final, are the same. If I chose the equation delta x is equal to 1/2 times the quantity v plus v naught times t, that's everything I need to solve for t. So I plug in the numbers, and I get 41,029.5 is equal to 1/2 times the quantity 30.56 plus 30.56 times t. But that's really 2 times 30.56, and 1/2 of 2 is actually 1. So the 1/2 will cancel with the 2, and that's going to leave me with 41,029.5, almost forgot my 0.5 there, is equal to 30.56 t, divide by 30.56 to isolate the t, and then I get a final answer of 1,340, oh wait a minute, 42 seconds, or 1,342.5 seconds. Now that's the time in seconds. What does that mean? That means that I have my little car and I'm traveling at a constant velocity of 30.56 meters per second. And so the car is traveling at a constant velocity from a starting point, and as it travels a total of 41,029.5 meters, and the amount of time it takes it to travel that distance is 1,342.5 seconds. Now we might be asked to convert that to minutes, but remember the SI units are in seconds. So that's pretty much our answer for part A. Part B wants to know if it stopped in 35 seconds, what would we do? Okay, so, oh, I forgot. Let's go ahead and convert that to minutes right now. So if I say t is equal to 1,342.5 seconds, then we could divide by 60 seconds on both sides, and we get the time is 22.5 minutes. Normally we would leave it in seconds, but this particular question asks us to write the time in minutes. Now let's go to part B. Part B says if the car is to stop in 35 seconds, what is the average acceleration needed to slow down the car? So now part B is a completely different scenario than part A. So part A is the car travels at a constant velocity, then we're figuring out how much time it would take at that constant velocity to reach a certain distance. Part B is completely different, okay? Part B, the car is traveling, then it slows down to a stop. So it's really like two problems in one. So all this information we don't really need, so we'll erase it. And we're starting with all brand new stuff. So what is the brand new stuff? Well, for Part B, let's list some things. Our initial velocity is 30.56 meters per second. If the car slows down to a stop, the final velocity is 0 meters per second. We know that the time that it will take is 35 seconds, and we're asked to solve for the acceleration. So we don't know what the acceleration is, so we leave that blank. But we are given that the time that would take is 35 seconds. So now I need a different equation that I can plug in all this information to and solve for A. Well, that equation is V equals V naught plus A times T. Plug and chug. I'm left with a bunch of numbers in the variable A. Using algebra, I isolate the A. I move the 30.56 to the other side of the equation, then I divide by 35. The 35 cancels, and what I end up with is that A is equal to negative 30.56 divided by 35, or negative 0.87 meters per second squared. Now the negative number represents the direction. So what that means is while my car is traveling to the right, my deceleration or the acceleration is going to be going in the negative direction. So it's going to oppose the direction of the velocity of the car. And that's pretty much it. So if we were to recap what took place, Part A, how long would it take time-wise for that car at 110 kilometers per hour to travel a distance of 25.5 miles? We get a time, and then a Part B, given the time, how long would it take us, or not how long would it take, but how much acceleration will we need to slow down. For our next question, it says consider a mass initially moving at 7.5 meters per second. Now mass could be anything. I like to use cars because cars are something that we think of moving, but it could be a rock, it could be a ball. Anything that moves is what we're talking about. And we're asked to figure out if it is moving with an initial velocity of 7.5 meters per second, how long does it take to move 3.5 kilometers if it accelerates at 0.55 meters per second squared? That's Part A. And then Part B is how fast is it moving after this acceleration? Or we're basically being asked to find the final velocity. So let me clean up the screen here a little bit. So I have my object. My object is traveling in this direction with the initial velocity of 7.5 meters per second. The distance that it's going to travel is 3.5 kilometers. Remember, that's 1,000 meters, so 3.5 kilometers is 3,500 meters. It tells us the acceleration is in the same direction because it's positive 0.55 meters per second. And then it asks us how long does it take, so we have to solve for time. So I look for a kinematic equation that has an initial velocity, an acceleration, and a time. So I could use delta x is equal to v naught times t plus 1/2 t squared. Let's plug in the numbers and then go from there. So my delta x, or displacement, is 3,500. My initial velocity is 7.5 times t plus 1/2 times my acceleration, 0.550 times t squared. That kind of looks like a quadratic equation. So if I set one side equal to 0, do some fancy maneuvering, in other words 1/2 of 0.55 is 0.275, t squared plus 7.5t minus 3,500, I have a quadratic equation that's representing ax squared plus bx plus c, where a equals 0.275, b equals 7.5, and c equals negative 3,500. You can't factor this quadratic. I mean, you could try, but the decimals make it kind of messy. So the easiest way to solve this quadratic equation is to use the quadratic formula. In other words, t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to plug in my numbers and then just using algebra slowly chip away and simplify what those values for t are going to be. I'm going to start, because we're going to do groupings first, so I'm going to start simplifying all the information underneath the square root symbol. In other words, 7.5 squared is 56.25. Negative 4 times 2.7 or 0.275 times negative 3,500 is a positive 3850, all over 2 times 0.275, which is the 0.55. Then I'm going to add the two terms under the square root, which add up to 3906.25, all over 0.55. Then I'm going to take the square root of 3906.25, which is about 62.5 roughly, over 0.55. And then by separating those two terms, I end up with t could equal 100 or t could equal negative 127. Now, the negative 127 seconds is something that we wouldn't do in high school, so not in high school will we ever mess with that. So the real answer that we're looking for is it takes 100 seconds to do that, or 1.4 minutes, I think is what that would convert to. So again, to kind of recap, what we were looking for was how much time would it take for a mass that's traveling at 7.5 meters per second travel a distance of 3,500. Now that's just the part A. So part A was the time that it took. To find the final velocity, which is part B, we use a different equation. The final velocity is equal to the initial velocity plus the acceleration times the time. And we just solve for the time, which was 100 seconds. When we plug and chug everything away, we find that the final velocity is 62.5 meters per second. So now we've completely answered the whole question. So it would take about 100 seconds, and our final velocity at the end of it would be 62.5 meters per second.